Now let's look at an example from the book. We are going to look at problem 513. Here we have this beam, and we want to determine the reactions at the supports. So we have two types of supports. In A, we have this contact, which is producing a force perpendicular to the surface, and in B we have a pin which is producing a force perpendicular, a force in any given direction. So A is producing a normal force, NA, and B is producing a force which can have any arbitrary direction. So, as I said, the first thing we need to do is to draw the free body diagram. It's very important. So, I'm going to draw my beam here, and then I'm going to put my system of reference, and for convenience I will put it in A. So I have Y and X. Now there are the forces produced by this distributed load. We can simplify this distributed load by looking at it as a composition of two distributed loads. A rectangular one, which is equal to all of this. So if you remember, a load is equivalent to the area of this representation. So the area is going to be given by 600, which is the height, times the length, which is 3 plus 3, so it's 6. And for a rectangular load, the centroid is in the middle, so this force is applied in the middle and is equal to 600 times 6. Then there is this second part of it, this triangle here, and the load is going to be equivalent to the area of that triangle. Now the height is 300 because it's 900 minus 600, so the area of a triangle is 1/2. The height 300 times the length, and in this case it's just 3. And the point of application is at 1/3 from the origin, or is 2/3 from this point. So I'll put it here, and this distance is 1 meter, and this is that load, so it's 1/2 300 times 3. And then I have my vincular, my constraint reaction, so I have Na and B, which is composed of By and Bx. So let's solve the equilibrium equation. Here I will put a better drawing. Alright. So my equations, I will start with the moments around A. So this is going to be the force produced by By, which is positive, times the distance, which is 6 meters. So this is 6 times By minus, because it's negative, the force, the moment produced by this component of the force, and is negative because I had put my system of reference like this. So Z is coming out of the paper, and the moment produced by that force is against Z, so it's negative. So that component is negative 1/2 300 times 3 times the arm, which is just 1 meter. And then I have negative minus the moment produced by this other component of the force, which is 600 times 6 times the arm, which is 3. And this for equilibrium has to be equal to 0. Bx is not producing any moment with respect to A because it's parallel to the arm of the distance. So the moment produced by that force is 0 because the angle between the arm and the force is 0. And Na is not producing any moment because it is applied exactly at A. So the distance between the point of application and the pole is 0. So the product of 0 by anything is 0, of course. So we can just solve this equation and we'll find that By is equal to 1875 newtons. Now, for to find the other reactions, I will solve Fy equals 0. So, what forces are acting on Y? There is Na, then there is By, that I already know how much it is, and then there are the two loads, so 1/2 300 times 3 minus 600 times 6, and this has to be equal to 0. If I solve this equation and I substitute the value of By that I found, I obtain that Na is equal to 2175 newtons. In order to find the Bx, we'll have to solve the equilibrium on X, but that's basically trivial because the only force acting on X is Bx, so the equilibrium will be basically just saying Bx is equal to 0. So the reactions of the pin in B is all vertical, and that's because all the forces acting on my system are vertical.